This is content of part 3. If you're interested only in specific part of this video, just jump to its start time. Next, I will talk about the analysis of the measured data. The data of this measurement method contains several different important pieces of information. The data analysis should be done in very specific and fixed consequences. Otherwise, a systematic error is possible. I suggest at first you use my data analyzing software and my measurement data of different nanomagnets, which both can be freely downloaded from my website. After you get the idea of how I do the measurement and understand features of measurement method, you can make your own analyzing software analyze your own measurement data. Analyzing software and the data of measured nanomagnets can be downloaded from my website. Just go to top part of content, slightly down, and just open downloading page. So for content, push measure anisotropy field program, and you can download zip file with all program files here. The program is fully free and open source. You can check and modify the programming code as you wish. There is an instruction how to unzip it and use it just on the top. Here. Also there is all measurement data for all nanomagnets. Just push here and different files correspond to different date. I suggest you download the most recent one. After you unzip the data file in a directory of your choice, you can see the folders with names of different wafers. All details about any specific wafer you can find on my website. From top content, just go to part number 6, and this all measurement data. For each wafer you can see its structure and some measured parameters. If you want to see more detail, just click on the wafer name. You can see all detail of the measurement data for this wafer. For example, if you want to see raw measurement data of the wafer named Ha.03, just go to the correspondent folder and you can see another folders. It's data measured for different nanomagnets. For example, Ha.65 means the right side, column number 6, row number 5 is one nanomagnet. SOT means spin orbit torque. It means the anisotropy field measured as function of current. The SMA means voltage control magnetic anisotropy. It means that anisotropy field is measured as function of gate voltage. AMR means the anomalous magnetoresistance. For example, let's see raw data for nanomagnet named Ha.03 as function of the current. So when you come here, first you see many files, and this files which is named start with Hani, it's the data containing raw data for this measurement. About the file naming, Hani means the raw data for anisotropy measurement. 90° means that the magnetic field is scanned perpendicularly to the current. It could be also 0°. 0° means the scan is along the current. M2 means the bias voltage. For this example, is plus 2 volt. Gate means the data of the gate hole probe. In a second I will explain the meaning of the name gate. This picture shows the design of my samples. There is a tantalum nanowire with iron-boron nanomagnet on top of it. There are 2 hole probes. The first probe is named gate, is connected to iron-boron nanomagnet. The second probe, which is named gap, is connected 10 micrometer aside from the nanomagnet. Some samples have a second nanomagnet fabricated on the nanowire 10 micrometer aside from the first nanomagnet. In that case, the gap probe is connected to the second nanomagnet, and it's named gap nanomagnet. The bias voltage means a voltage applied between 2 ends of nanowire. In the case of VCMA measurement, a gate voltage is applied between gate electrode on the top of nanomagnet and one side of nanowire. There is a thick M0 gate between the gate electrode and nanomagnet. Therefore, there is no current through the gate. The M0's thickness is about 7 nanometers. This raw data is just text file. You can open it with any text editor. So let's just click on it. And you can see it's open. So this top row is just perpendicular magnetic field which change from -7 kilogauss to 7 kilogauss. This left column corresponding plane magnetic field which change from -2 kilogauss to 2 kilogauss and back to -2 kilogauss, and that is corresponding measured Hall angles. You can draw just this file to any your plotting editor, for example in my case into Origin, and you can do it in Excel. So you can see this is perpendicular field, this is in plane field, and that is the correspondent measured Hall angle. So you can plot any data. So you see, and you can plot many data together like this. So slope is different. As I already explained about this measurement, so for each fixed perpendicular magnetic field and plane magnetic field scan, in my case from -2 kilogauss to 2 kilogauss. So that is a scan in plane magnetic field, x-axis. And such scan is done for different values perpendicular magnetic field, which is from change from -7 to 7 kilogauss in my case. So for each fixed perpendicular magnetic field, in-plane field is scanned and Hall angle is measured. So if we look like from small magnetic field to bigger magnetic field, so you can see that the small magnetic field, the more we have larger than we have perpendicular magnetic field, so change become more slower. So as a result we have that is the in-plane magnetic field, and plane in kilogauss, that is the Hall angle, in millidegree, and that is as perpendicular in kilogauss, 0.2 kilogauss, 0.8 kilogauss, 0.1, 1.5 kilogauss to 0.5 kilogauss, and so on. The goal of this measurement is to evaluate the anisotropy field with high precision. For this purpose, this important linear relation between the in-plane component of magnetization and in-plane component of external magnetic field is used. This relation is for in-plane component of the magnetization, but the Hall angle which we measure is proportional to perpendicular component of the magnetization. The Hall angle is the largest when magnetization is perpendicular to the plane and becomes smaller when the magnetization is tilted. From this relation, the perpendicular component of magnetization can be easily found just by normalizing the Hall angle to its maximum value. The in-plane component of magnetization can be found from perpendicular component from this Pythagorean equation. Next, I will talk about step number 1 of processing measurement data. The task of this step is to remove the systematic error number 1. The error is due to the slight misalignment of the Hall electrodes. It is absolutely impossible to fabricate an absolutely perfect Hall bar. There is always some misalignment. For example, in case if this left electrode is slightly above the right electrode, even in absence of any Hall effect, there is a difference in electrical potential between electrodes, and therefore there is some voltage between electrodes. This unwanted voltage should be separated and removed from the measured Hall voltage. In contrast to the Hall voltage, this voltage does not change with a reversal of magnetic field. Therefore, comparison of measurement data measured for two opposite directions of perpendicular magnetic field can remove this unwanted voltage from the measured Hall voltage. In our measurement, in which the in-plane magnetic field is scanned, it's necessary to remove the systematic error due to this unwanted voltage without a reversal of the perpendicular magnetic field. For this purpose, the Hall angle measured at zero in-plane magnetic field is subtracted. Zero magnetic field is subtracted from Hall angle measured at other value of in-plane magnetic field. You see. So in fact, only the change of the Hall angle with applied in-plane magnetic field is important for this measurement and recorded in this file. In separate measurements, the value of maximum Hall angle at the perpendicular magnetization is measured with a high precision. So, if you like to use my data analysis program with your measurement data, you need to prepare your data in this format. In-plane magnetic field for different value of perpendicular magnetic field and the Hall angle difference from its maximum value. Second systematic error is error due to magnetic field induced by spin accumulation. The reason for the problem for the fitting is the existence of one additional magnetic field, which I assign here as offset magnetic field, and which is created by spin accumulation. I will talk about this magnetic field just a minute later, but here you can see the problem. In the absence of this additional offset magnetic field, the measured dependence would be described like this. In reality, the offset magnetic field is present. As a result, the linear dependence looks like this, with this part. And the measured dependence of Hall angle, in fact, described by this formula. There is no wonder that one gets a systematic error when trying to fit the measured data described by this formula using a very different formula like this. Therefore, it's only possible to evaluate the anisotropy field correctly when the value of offset field is already known. How to evaluate the offset field from the measured data I will explain in the next part of this video. The reason for that is the existence of additional magnetic field which is induced by the accumulation of spin polarized electrons. This graph shows the expected dependence of Hall angle on the external magnetic field in case when there is no additional in-plane magnetic field. It is critically important that data is absolutely symmetrical for polarity reversal of scan in-plane magnetic field. Iron cobalt nanomagnet is amorphous and has this isotropic in-plane symmetry. Only another source of the magnetic field may break this symmetry. This graph shows the measured data. The data is still symmetrical, but the symmetry center is offset from the center. It can only occur in the presence of another in-plane magnetic field. This magnetic field is induced by spin-polarized electrons, which are accumulated due to the spin-Hall effect. I will talk about it in more detail later. Now, I would like to explain how to measure this field with high precision and how to exclude the systematic error due to this field for the measurement of the anisotropy field. This graph explains the fitting methods to evaluate the value of spin accumulation-induced magnetic field. The positive and negative parts of measured data are fitted to each other with the offset magnetic field as a parameter. The magnetic field is found when the mean square difference between parts is smallest. These methods give a very high measurement precision, which is evaluated to be about 0.1 to 1 Gauss. So after the spin accumulation-induced magnetic field is measured, and therefore the measured Hall angle is symmetrized, the dependence of evaluated in-plane magnetization component on the scan external magnetic field becomes perfectly linear. You can see it here where dots are measured data. The anisotropy field is evaluated from slope of the linear fit of this data with a very high precision of about 0.1 to 1 Gauss. If you are interested to see the content and other parts of this video, you can find the links below this video.